Kia ora, Year 13 and Year 12. This is a really good question from the 2015 paper, and it's all about bus breakdowns. So the first thing we're going to look at is which distribution we'll apply. And in part 1, it's a pretty straightforward question. In part 2, I really want you to make sure that you pick up a pen and try to write out your answer before I go through it. If you're the kind of person that goes, oh no, I'm going to skip that bit of the video, please don't, because this is the kind of question that you see a lot of at level 3. And it's a really nice example. Okay, so we'll start off. We've got a local authority has been monitoring the number of bus breakdowns over a long period of time, and they've found that the mean number of breakdowns per hour is 0.3. Right, so we're thinking about which of our 5 distributions it's going to fit. So we've got binomial, uniform, normal, triangular, and Poisson. Right, bunt P. So it's definitely going to fit the Poisson distribution here, if you had to pick one of them, because we're given a number of something, so a discrete thing over a continuous interval, which here is time. So we're working with a binomial, and we've got lambda equals 0.3, but be careful because that's per hour. Okay, and the operations manager uses a Poisson distribution to model the number of bus breakdowns. So they even tell you which one it is. Using this model, calculate the probability that there are no more than 2 bus breakdowns during any 4-hour period. So the first thing to do here is to change that lambda to per 4 hours. So we times that by 4, we times this by 4, and we get lambda is equal to 1.2. No more than 2 bus breakdowns means that we want the probability that x is less than or equal to 2, where x is equal to breakdowns per 4 hours. Can't spell today, can't do maths and can't spell. There we go. So grab your calculator and you want to go to dist, menu, stat, where are we? Menu, stat, dist, over to Poisson, and then PCD. Make sure you're in variable, and the answer we should get is equal to 0.8795. Okay, so that's an achieved tick. Right, finding a simple Poisson. The next thing we're asked to do is to give any assumptions that need to be made. So assumptions for the Poisson are the following, but we've got to put them in context. The first thing is that we have to assume that the thing happens randomly. So we're going to put that first. Assume that breakdowns occur at random. Please, if you're sitting there watching this, can you write these down? Give it a go before you watch this bit of the video. There's no point just listening to it. In the exam, you've actually got to put your pen on the piece of paper. Okay, next thing we're going to assume is that the bus breakdowns happen independently of each other. So independence is an assumption. If you write independence, it doesn't tell the reader anything. So assume that breakdowns are independent of one another. All right, what else? Well, we're going to assume that we can't have simultaneous buses breaking down. This, I always feel, is the silliest of the assumptions with the Poisson, because if we made our time interval finer, we could almost certainly not have this be a drama. So it's just an assumption. It's not a problematic one. Assume we can't have simultaneous bus breakdowns. And the last one, and the one that's probably the worst of the assumptions, is that we're going to assume that the rate of breakdowns per 4 hours is constant. So no matter what time. Right, and so we can see that that's pretty stupid. We're actually going to be able to use that later on in the last part of the question. Now, to get merit here, all you had to do was this. I'll just pop the schedule up. You didn't have to have all of them, right? But you had to have the probability done correctly. And then this is the short version of the 4 assumptions, and you had to give 2 of those assumptions in context. Okay, so that's the straightforward bit of the question. Here comes the next bit. Now, the reason I like this is it's got real-life data in it, right? So we've got the bus operations manager has done a graph of the data collected on the number of breakdowns during 12-hour periods. And this is the experimental distribution. So you know, even before you read the question, what are you going to have to do? You're going to have to compare actual or experimental, to theoretical, which we call the model distribution. Right, so we have to discuss whether a Poisson distribution is a good model for the number of bus breakdowns for any 12-hour period. And as part of your discussion, you should compare the features of the experimental and model distributions. And you can draw on the graph above, but then you've got to talk about those probabilities in your working below. Okay, so pause the video here and take a good 5 minutes and write down a full answer on what you'd say here, and then I'll go through it. Okay, so hopefully you've had a chance to write some things down, and so have I. The thing I'm going to do first is show you what my answers look like. Then I'm going to come back and go through where I got all the numbers from, because this is a question where you can get into quite a lot of great detail. For excellence, what you had to do here was to have the following things. So here's the schedule, but it doesn't really discuss it as much as I'd like to. So you can see there's all kinds of stuff written here. It's a bit of a messy cut and paste job that I've done, but they've got some useful headings, and I'm going to give you some as well. So to get excellence in this question, you had to have the following things. You had to have one discussion point based on comparisons between the experimental and the model, so the actual versus the theoretical, with numerical values used. So if you can calculate some basic probabilities, that's what you've got to do and link it into the context. Then you had to have a discussion point about either another comparison, so two number comparisons, or picking up that one of the assumptions of the Poisson model was bad. And overall, you had to make a conclusion. Okay, so the main thing here is make sure you answer the question, because you needed to do that for merit as well. Okay, if you want a little achieve tick here, all you had to do was one thing without numbers, comparing the experimental and the model. Okay, so let's have a look at what I did. Right, so I've broken it out into 5 different things. And the first thing, and I think the thing that you should do to give yourself the most confidence, is to remember that in a Poisson distribution, we have the variance equaling the mean, right? So if we're modeling with a Poisson, way back when we first did it, we had this, that E of X was equal to the variance of X, and they were both equal to lambda. So what we can do is take our data and figure out what's the expected value, what's the average, and then we work out the variance. And we see that the variance is much higher than it should be. So I'm going to show you the graph for that so you see what I'm talking about. What you're doing is you're taking these numbers and you're working out these probabilities, okay? And you're going back and you're doing E of X is the thing where you go 0 times blah, blah, plus 1 times blah, 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 and so on. But I promise I'll put those calculations in soon, but I'm going to just keep going through the discussion first. Right, you do that and you do the same thing and you calculate the variance. So if the Poisson is a good fit, what you should find is that those two numbers are pretty similar. But in here, they're not. They're miles apart. So that's a big problem. And that's the best thing to say first of all. The next thing to say is that when we have a Poisson, it should be unimodal. Right, so our Poisson distributions are not symmetric, but they should look, depending on what your lambda value is, something like this. So when lambda is small, you'll get quite an asymmetric kind of curve. But when lambda is big, it will get more symmetric. But in any case, it's going to be basically unimodal, whereas our data here doesn't fit that shape. Where's it gone? Here we are. So we can see we've got a mode around 1, and then we've kind of got another bumpy thing happening here. We certainly don't have the pattern of this or this. Right, so then the next obvious thing to do, and it even hints at this, is to just get your calculator and put the numbers on, okay? So if you do that, you've then got to use them in the question. So to do that, you need to go to your calculator, go to distributions, stat, dist, let's see. But this time we want to use list when we're in the Poisson distribution. So you're going to go into PPD to get the individual probabilities. So dist, arrow, Poisson, PPD, put in your mean that you've worked out. Your mean is 3.62. And then in your list, you can set up from 0 through to 9. And then you can plonk all of the approximate values on. Right, so we're going to put model in red pen or something like that. So we can draw the actual model distribution on, and we're going to see some big problems. So I'm going to draw it in pink. All right. Okay, so I paused it so you didn't have to watch me drawing them all on. But you can see that we've got a real issue with the theoretical model. And what you have to do is talk about what the problems are. So you can see that in between 2 and about 6, the model is way too high. Right? So the model is over predicting the number of breakdowns between 2 and 6. But at the other ends, the model is too low. The model is under predicting the number of breakdowns of 0 or 1 breakdowns, or 7, 8, and 9 breakdowns. So when I've written up some shorthand for you on that, this is what I've said. Where's it gone? Okay, we've done shape. Yep, shape again. Put the values on and just show that they don't fit. And the model is over predicting for 2 to 6 breakdowns, and it's under predicting for others. Right, the next thing to talk about is that there's a constant rate assumption that we have when we're doing a Poisson, and that is a big problem here, right? Because you must put it in context. Why is it a problem? Well, how many bus breakdowns happen between 2 in the morning and 7 in the morning? None, because there aren't any buses. Okay, so that's a bit of a drama. So overall, what you've got to say is that the model is a bad fit. Now, here goes the last little bit where I do the numbers, and you're going to read them off the graph. Now, don't stress out about getting every single probability read off correctly. I'm going to try and find the graph. Where's it gone? Right, here's the graph. So you want to do this quite early on when you're doing a question like this before you draw all over it. But let's just figure out what we think these numbers are. So this one here is 0.11. This one here I'm going to have is 0.15. This is 0.14, and so on. So you can do this, as you know, with your calculator, or you can do it by hand. Now, I've done it by hand here. And there's another video from the 2017 paper where I go through this, but let's work out what E of X is here. Well, E of X is going to be 0 times whatever, plus 1 times 0.15, plus 2 times 0.14, plus 3 times 0.14, plus 4 times 0.12. So if you're writing this in your exam book, just write down ... like this, and do it on your calculator. But make sure the examiner can see what you've done. So after you've done all that, I got 3.62, which I think is about right. You might have mucked one of these up, but it just won't matter. So that's E of X. Now, to find the variance of X, remember what I have to do is this thing here. I have to get E of X squared minus E of X all squared. So we're going to have something here, take away 3.62 squared. So to get the E of X squared, instead of using 0, 1, 2, 3, and 4, I'm going to replace them with, well, 1 actually stays. This will be 4, this will be 9, and this will be 16. So this is one of those skills that we did really early on in the year when some of you weren't paying that much attention, but it's an important one. So the variance of X is going to be equal to 1 times 0.15 plus 2 squared, 4 times 0.14, plus 9, 3 squared times 0.14, plus plus 81 times 0.01, right, so this is my 9 squared, take away 3.62 squared, right, so that gives me here the number that I used earlier of 5.79. Okay, so that's where those numbers come from. Leave me a message or send me an email if you want me to go through this slower. I've done this video in a big hurry just to get it done before the exam, so I know it's not that well structured, but hopefully it's going to help. Now, if you are looking at this stuff here and you're going, I have no idea how to do that variance, then go and grab your Walker book for, I think it's in the probability concepts one, and go through some easy examples in there. Or go and watch 2017, and it's question 2A. So there's a video on that that goes through this calculation here again. Thanks for watching. I'll do some more later, and send me an email telling me which ones you want me to do.